Start recording so Jada doesn't yell at me and say record, Miss Baskin. Okay. So today we're just going to kind of reset where we ended last class. We're going to finish the notes and do the practice problems that are in here. And then I will remind you of what's due on Sunday, and that's it. So, ooh, excuse me. So let's go ahead and get started. Okay, so from last class, when we look at these diagrams, do you remember where are we imagining the nucleus in the graph? Left,
On the left.
right, where?
Left.
Left. Okay, so we are imagining that the nucleus is on the left. It's basically, several people wrote, it's at the origin, right? It's like at the graph origin. And that's a good way to think about it. So which of those two things is going to require more energy to remove? An electron from 1s or an electron from 4s?
1s.
Yes. Why?
It is closer to the nucleus,
Yep.
and because of that, it has a stronger attraction to.
Exactly that. Okay, so the 1s will require more energy to pull an electron off because it's closer to the nucleus, which means it's feeling a greater sense of attraction. All right. Okay, and then do we remember, what does the size of the little peak in the graph tell you?
Relative number of electrons.
All right, number of electrons. Bam. Number of electrons. So if we look at one of these, so again, we are imagining that our nucleus is right here. So you can imagine, right, that is our big nucleus is right there. And so if you imagine that's where the nucleus is, the closer you are to that, the more attraction you're feeling, because, right, all of these peaks represent negative electrons. So, and the more attraction, the more energy there is. So that's why these numbers down here are in opposite order, right? So they start with the big numbers and then go down. So you have to kind of remember when we're doing these, it's helpful to remember the order for electron configuration. That is going to help you kind of remember what these are, but remember that our energy level numbers start close to the nucleus and go up. So this first peak would clearly be 1 because it's closest to the nucleus. 1 only has an s. And the height of this line sets the height for 2 electrons. So that's 1s2. So all of these are the exact same height, which means all of these represent 2 electrons, right? Those are all 2 electrons. And since those are all 2 electrons, you know what? The only sublevel that holds only 2 electrons is s. So these all represent an s2. All of them, because they're exactly the same. So then the only thing you have to realize is that they're each a different energy level. So if this was 1s2, well, this has to be a 2s2, and that would be a 3s2, and that would be a 4s2. And then if you look at the, dark green. And then if you look at these taller peaks, you can imagine that you've got 1, 2, 3 times this shorter peak here. So that means this must represent 6 electrons. Now, they did actually have over here number of electrons, but they don't always. Sometimes they just say relative amount or something. They don't always specifically identify. But this would represent 6 electrons because it is 3 times this smaller red line. So P is what holds our 6 electrons, so that's a P6. This is the same height, so that must be a P6. This is going to be a 2P, and therefore this is going to be a 3P. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now this is already telling you that this is calcium. But that's our configuration for calcium: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And it just goes left to right in the exact same order. So one of the things we're going to do in those notes is actually rewrite the order of this electron configuration. We don't normally do PES diagrams for elements too much larger than calcium. So you don't have to memorize very much of this configuration order. Normally this first chunk right here is enough. The 1s, 2s, 2p, 3s, 3p, 4s is enough to get you going. And then you should just, if you imagine those peaks as electrons, it does start getting easier to be able to do this. Okay, so with the people who've just popped in, now the only people I see missing: Sophia and Manny from 2nd period, Eliora, Dalia, Shayla, Josh, Jayla, Sabrina, and Jada from 4th. So, okay. If anybody wants a picture of that really fast, take a shot, because I'm about to clear it off and move on. And drink more of my lovely coffee. Ah, tasty. I am one of those people, in case you're wondering, who does still drink hot coffee in the middle of the summer. This should not surprise you in the slightest. Okay, so we're gonna finish up these notes because we did 3 pages of them, I think, or 2 pages. I don't remember what we did. And we're gonna finish them up, all that stuff. Okay, so switching over. There we go. Okay, so that's where we ended last class. That was at the bottom of a page. We just kind of reviewed all of that. So at the very top of this, why don't I go ahead and rewrite that electron configuration order so that you have it in one place involved in this PES stuff. So it was always 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. That's enough of the order. You're not going to ever need beyond that for any of this sort of stuff. In general, for AP chemistry, they don't ask too much about super large elements unless they're asking you to just predict what the very last portion is. So, okay. So now let's look at this. It says here on the left, we've got the PES for neon. How many electrons does neon have if I look at the periodic table?
10.
10. Okay. So if I had asked you last week to write the electron configuration for neon, what would we write?
1s2, 2s2, 2p6.
Okay. So we know from last week, that's what the electron configuration is. So all we have to do is assign that configuration to these 3 peaks. You should recognize that I've got 1, 2, 3 portions of my electron configuration, and I have 3 peaks. You're always going to have the same number of peaks as you have energy level sublevel combinations in your electron configuration. So if I am again imagining that my electron or my 10 protons in my nucleus is right there, right? It's always there at the origin. Then I simply need to say, okay, so that means that this goes there, this goes here, and this goes here. And that should make sense because my 1s2 is going to be closest and is always going to have the highest energy. So this guy here has the highest energy, and the highest energy means it's closest to the nucleus. This guy is the same size, and if it's the same size, then it's got the same number of things. So that's how you always know it's going to be an S2 as well. And then this guy is about 3 times as tall, which is how you know it's a 6. Now, there are times where you may have to kind of estimate, oh, is that more like 5 or is that more like 6? But they'll try and make it obvious if you're having to figure that sort of thing out. There's one more thing on this diagram I want to point out, and that is that break right there. Have you ever seen that in a history timeline?
No.
It may have been there, you may just not have noticed. But when you put that there, it's a break in the scale. So really, you've got 90,000, 80,000, and then you jump all the way down to 5,000. In reality, this second peak here, that 2s2, is way off the page to the right. It's but if we want to actually make a graph that will fit on the paper, we break the scale and condense it. There's just a huge gap there. So you sometimes see that in history timelines when we're talking about ancient time. It's like, well, there was this. And then 20,000 years later, there was this. Well, instead of having a big, long break of nothingness going on, we do the little slash lines. For our purposes, however, those little breaks are a good indication that you are changing energy level numbers. So you have a first energy level and then a set of break lines, and then we're in the second energy level. And I'll point out on the other diagrams that every time there is a pair of those slashes where you have a break in scale, you switch energy level numbers. So that's another good visual cue when you're looking at these graphs. Okay, so we've identified what the peaks are, 1s2, 2s2, and 2p6. So if I look at these 2 possible Bohr diagrams on the right, which one of those matches the number of peaks we saw? The one on the left or the one on the right?
The one on the right.
Yes, this guy. Because the one on the left would give you how many peaks?
2.
2. This would be only 2 peaks.
Wait, why is it 2 peaks?
Because it's only got 2 circles. Right? Because basically a peak is when you have things of the same energy. So all of these 2 have the same energy. and then all of these have the same energy. So you'd have a peak of 2, and then you'd have a peak of 8.
Oh, okay.
Okay. And then this one here, you're going to have 3 peaks, right? You'd have a peak of 2, a peak of 2, and a peak of 6. And that is what we see. So it was this type of experiment that let them see that there weren't just energy levels, that there were actually sub-levels in the energy level, that we need to break up the second energy level into 2 parts because it does provide 2 different peaks. Because Bohr was too simple, is what it came down to. Okay. So I'm gonna scoot up just a little bit. Okay, so we've got 2 new spectrums. One is for phosphorus, one is for sulfur. They have very nicely labeled them for us so we don't have to guess. Phosphorus and sulfur. How many electrons does each one of those have?
15 for phosphorus, 16 for sulfur.
All right, so we got 15 and 16, so we've done that. And then we want to label all the peaks. So again, I want to draw your attention to the breaks here. That kind of sets you off and lets you know we're talking about the first energy level, the second energy level, the third energy level, right? Every time you have one of those sets of breaks, it's a change in energy level. So if I'm following this configuration pattern at the top, left to right, assigning to these peaks, that is not what I meant to do. There we go. Assigning these peaks, my first peak is always, so peak A is going to be what am I going to label this guy?
1s2.
1s2. And they're both 1s2 because the first peak is always 1s2. Always, always. And then we've got a big break telling us we've switched to the second energy level. And you will notice that there's always a very short peak followed by a very tall peak because S is always then followed by P. So for both of these, B and C then follow as 2s2 and 2p6. And again, I'm noticing that A and B and D are all the same size on all of these. So when I see another set of breaks in the line, and I know I switched to a higher energy level, so I've got a set of line breaks, which is telling me I've gone up to 3, but the size of this D peak is the same as the A and the B, which means it's also an S2. So if you look at the E peaks, they are more than 2. This is where sometimes you have to kind of estimate to see what it is. Now, they've told you it's phosphorus and they've told you it's sulfur, so we know what they are because we already know how to do electron configurations. But if we start with this phosphorus one, if I look at E, I can tell that it is slightly more than D, but it's not twice as big, right? So the D peak kind of hits over to there. So you can imagine that this is like 1, 2, this is like 1, 2, 3. So I'm going to estimate that this E peak holds 3 electrons. That's kind of how you have to do it. It's not an exact science, it's just kind of a rough estimate. And since we're still in the third energy level, we know that E then must be 3p3. And sure enough, yes?
I mean, can't you just, like, since you already have everything before that and you know it's 15, just add up what you have and then.
Yes, but what I'm saying is most of the time, the way these questions are framed, they'll give you a spectrum and not the element, and you have to figure out what the element is.
Okay.
So yeah, but you are correct, yes. So, but if I look at sulfur, that's where this one hits. And if I kind of cut that in half, I'm like, all right, so that's 1, 2. This would be 1, 2. That's more than 3. It would be like 3, 4. Okay, so you just kind of eyeball it that way. And 3p4. Okay, so we've got our protons, our electrons. We've labeled all of the peaks with the electrons for everything. Okay, so I'm gonna erase some stuff down here at the bottom to make it a little bit easier to see these numbers. Because I want to point out, the next question says, why do the peaks of sulfur seem to be shifted left than the peaks in the phosphorus? So A for phosphorus is about 200, but A for sulfur is between 200 and 300. Peak B is just a little bit after 20, but it's squarely between 20 and 30 here. So all of the peaks for sulfur are shifted left. So what is it that is making that happen? And first you have to understand, what does it mean to be shifted left? Shifted left means that you've got more energy required to remove an electron. That's what it means to be shifted left, right? It means a higher ionization energy. So why would it require more energy to remove an electron from sulfur compared to phosphorus?
Sulfur has more protons, so they're exerting a greater force over all of the electrons.
All right, so I'm using P plus for proton because I just want to save space. So sulfur has more protons than phosphorus. So they have more attraction to the electrons, requiring more energy to remove. So it is this fact right here that is super easy to see when you watch the Edpuzzle video, because he goes through the first 20 elements where the graphs are lined up exactly on each other. And as he goes through them quickly, you can literally see all the peaks dancing to the left as he keeps going. So it's really obvious that as you add more protons in the nucleus, you've got more pull, more attraction. So that's why we say it's really helpful to imagine that the nucleus is right here, because the nucleus is literally pulling the peaks towards itself as you stick more positive protons in there. So that's why that kind of visualization is very, very helpful. You've got 16 positive things there, but you only have 15 positive things here. That one little proton, while it may not seem like very much, it is enough to require a little bit more energy to remove. This is the whole kind of concept we're going to kind of keep talking about over the next, the last 2 weeks is attraction between protons and electrons and how that makes so many different things happen. So the last question actually has us look at, clear all this off, these last 2 peaks. So I want to highlight what we've got going on here. Okay, So if we were to continue following the rule that we wrote in black on the question right there, we would imagine that this E peak for sulfur, we would think it should be shifted way over here, because everything in sulfur is shifted left, shifted left, shifted left. But that is not the case. This is not over to the left. It is actually pushed a little bit to the right compared to the E peak here, which is weird. All right. The entire reason that is happening is because of the other thing that happens with electrons. So electrons are going to attract to protons. However, electrons are going to repel from themselves, right? They are going to repel from each other. So what you have to imagine is that I've got all of these electrons here, all right? So this 3p4, you have to remember that p has 3 orbitals, right? 1, 2, 3, and then that one comes back 4. What are these 2 electrons doing to each other?
Pushing each other away.
All right, they are pushing apart. And what does it look like these 2 peaks here are doing to each other? They're
Pushing
also
each other apart.
pushing each other apart. So peak E is shifted slightly right. And again, slightly right means less energy required to remove an electron. So why would it require less energy to pull off an electron out of E for sulfur? Because they're already pushing apart. They're already trying to get away from each other. So they're like, no, 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 I don't want to be next to you. Take me, get me out of here. Okay. So sulfur has paired electrons in 3p that are already repelling from each other. So it's easier to remove that one. All right, it does end up being slightly easier to remove that paired electron in sulfur because it's being forced to share with somebody it doesn't want to share with. Okay, so this last thing is like, let's try and sketch what chlorine would look like. And the first thing we need to think about is how many electrons does chlorine have?
$17.
17. Okay, so I've got 15, I've got 16, so I'm just going to do one for 17. That's not that big a deal. It's just a little bit more. Okay, so that means my spectrum here, my graph is going to look about the same, right? So I'll even try and put breaks in about the same spot, right? 300, 200, 100, 30, 20, 10, and then do 2, and whoops, not 11, 1. Okay, so if I look at this first peak, for phosphorus, it was over the 200. For sulfur, it was just to the left of 200. So if I've got 17 protons right here, that first A peak is going to be even shifted further to the left. It doesn't have to be beautiful, but I know it's even further to the left. It's more like smack between the 300 and the 200. And then my B peak for phosphorus was just left of the 20. It was pretty squarely between the 20 and the 30 for sulfur. So it should be even closer to the 30 for chlorine, but about the same height as A. That C peak was between the 10 and the 20 for phosphorus, smack in the middle between the 10 and the 20 for sulfur. So it should be almost over the 20 and about 3 times as high. So something like that. Again, not trying to make it perfect. Then D for phosphorus was just to the right of the 2. It was directly over the 2 for sulfur. So it should be to the left of the 2 for chlorine. And then the last part for E, I have to have 5 electrons now. So it needs to be not quite as high as my C peak. And I don't have the massive amount of repulsion thing, so I'm still going to be to the left of the 1.0, but all of these, phosphorus and sulfur and chlorine, are all going to float around this 1.0 spot. So that last peak is not quite as tall, and it looks something like that. Now, is this a skill that normally AP asks you to do, to draw one? No, they normally just have you analyze these things, but it is kind of helpful to be able to do that and to look at that. So, because the things to note is all the peaks shift left because chlorine has 1 more proton. And then the last peak is slightly taller because it has 1 more electron. Okay. So let's look at these practice questions. And these practice questions are very similar to the practice website that is listed for a completion grade, as well as for some of the questions on the actual Google Doc assignment for the week. So I want to make sure we go through them so that you have this to be able to look at later if you need a refresher. So this first one, it says, which element could be represented by the spectrum below? So you will notice on the left-hand side on this axis, there is not an actual marking of numbers telling you the number of electrons, but there are these lines, vertical lines going across to help you compare. So you know that this first peak always represents what energy level and what sublevel.
1S.
It's always 1s. So that means that this is 1 electron, that's 2, that's 3. It kind of tells you that, right? So that's 1 electron, that's 2 electrons, that represents 3 electrons. So that's 1s2. So this peak must be
2S2.
2s2. And we know from the pattern that 2p comes next. And since this peak hits this mark, how many electrons does it hold?
Wouldn't it only be 3 because of where the line is?
Yes, it's 3. So 2 plus 2 plus 3 is atomic number 7, which is nitrogen. So that's how you use the lines in the graphs to kind of help you figure out those markings there. Okay, so if you need to take a picture of this, because I'm about to turn the page, my virtual page. Okay, so this next one, I've got two different spectrums. It's telling me I've got lithium and beryllium. Which of the following best explains the positioning and intensity of these peaks in this spectrum? So positioning is referring to left versus right, and intensity means the height or the number of electrons. So if I'm trying to compare two different elements, I should think, what are their atomic numbers? Because that's always going to be something here. So what's the atomic number of lithium?
3,
3. And beryllium?
4.
4. Okay, so I know that if I'm 3, that my configuration is 1s2, 2s1, and that if I'm 4, I'm 1s2, 2s2. So beryllium is shifted to the left versus lithium, and it is twice as tall. So which of these answers explains why beryllium is shifted to the left and why its peak is twice as tall? So which answer seems the most reasonable, A, B, C, or D?
Can you just explain what you said one more time?
What?
Can you just explain what you said one more time?
Yeah, I just asked which one of those answers is right. Which one explains why this peak is moved to the left and is twice as tall as this peak?
A.
It's A. The easiest thing is because it's got more electrons. All right, that's the only one that talks about the fact that it's got more electrons. Greater nuclear charge means more protons. So beryllium has both more protons in comparison to lithium, and it's got twice as many electrons in its S compared to lithium. So that's why it's A. So then looking at the next set, oops, got phosphorus and sulfur again. And then the question is, given the spectrum for phosphorus and sulfur, right? Phosphorus and sulfur, which of the following explains why the 2p for sulfur is left than the peak for phosphorus, but not for 3p? So we essentially just answered this on the previous page. So again, sulfur has 16 protons. Phosphorus has 15 protons. So everything for sulfur is shifted slightly, slightly, slightly left, always because it has a greater nuclear charge. Okay? So it's going to be either answer A or answer B. And then we have to look at the second part. The 3p is further to the right. Again, this one is shoved slightly to the right of what we would expect, and that is because of the repelling of those electrons. So which answer would that be? A again, electron repulsion. So this next question is another one comparing two different things. You've got sodium and potassium. All right, which one is going to explain the difference in energy here? So sodium and potassium are stacked on top of each other on the periodic table, what's the atomic number for each one?
11 and 19.
11 and 19. So while that does mean 11 and 19 electrons, that also means 11 and 19 protons. So phosphorus, these are both representing 3s, so phosphorus is way shifted over to the left because which one of these, A, B, C, or D?
A.
A. Because again, nuclear charge is just another way of saying more protons. Okay. And then let's look at the last couple of questions. So snap a picture if you need to. Okay. And what was I going to say? All right. So this is still looking at potassium and sodium. And this one wants to talk about the signal intensity. That again is the number of electrons. So if you imagine, we just said that sodium has 11 and potassium has 19. So if I look at these peaks, how many electrons are in the 3s peak for potassium? That little peak represents how many electrons?
2.
2. And this little peak represents how many electrons?
1.
1. So what answer seems to make the most sense here about why sodium only has 1 electron in its little peak versus potassium has 2 if they're both in that 3s?
See?
Yep. Those are their electron configurations. And when you look at it that way, if we're looking at the 3s peak for both of these, it's the very last thing you write for sodium. It's its last electron, but it's in the middle of the electron configuration for potassium. Okay, so looking at 6 here, I've got this whole big thing, and this tells me this is scandium, which I'll tell you is element 21. And it says, why does scandium make a 3+ ion instead of a 2+ ion? And this is related to the valence electrons. So I'm gonna tell you, if we assign all of these peaks, this is 1s2, 2s2, 2p6, 3s2, 3p6. This one is 4s2, and this one down here is 3d1. Now, when you watch this in the video, you'll see that the 4s peak appears first, and then that little 3d peak appears. So the 3d does fill after the 4s, but if you will notice, they are practically the same energy. And since they practically have the same amount of energy, scandium, along with many other transition metals, actually lose both of these because their energy is almost the same. Right? 0.77 and 0.63, those are almost exactly the same. So that makes the answer that one. All right, there's a very large difference between these two guys and this next one here. So big difference that way. And then the very, very last question tells you this is magnesium. And it wants you to imagine what aluminum would be. So magnesium has how many things?
12.
12. And aluminum? One more. So if it's got one more, that means every peak is shifted to the left to begin with. So the first thing you can do is just start by redrawing all of these peaks slightly shifted to the left. That handles 12. Where does aluminum's 13th electron go? Because these are 1s and 2s and 2p and 3s, which means that's full. So where does the next electron go?
To the right.
To the right. And is it going to be the same height as this peak, taller or shorter?
Shorter.
Shorter, because it's going to represent 3p1. All right, so that's the last thing in the practice. So take a picture of that if you need to, and I'm going to switch back to my slide deck and go over what you need to do for Sunday and put up the exit ticket. Okay, so for Sunday of this week, if you didn't do it for this morning, and I think almost half of everybody did, you need to do Ed Puzzle video 32. You need to fill out the exit ticket on the next screen. So again, doing the Ed Puzzle and filling out the exit tickets, that's what makes up your participation grade. No reason not to have a 10 out of 10 there. You need to do the practice quiz. So this is another one of those just do it for completion sort of things. So it's on a website. The link is on the assessment, not the assessment, the practice and application assignment on Google Classroom. So just take a picture of it. When you're done, you can do it as many times as you want. It's very similar questions to the ones we just went over here at the end. But that'll help you for the last thing you have to do, which is the Google Doc assignment that's in Google Classroom. So you do not want to start this on Sunday because you may not be able to get a hold of me if you have questions, because Sunday is my go hiking day and I'm gone all day long and I don't respond to any messages until Sunday night. So I would take a look at this today. Tomorrow at the latest, so that you can send me emails or chats or request some office hour time to be able to go over stuff. So the last thing is the free response questions for extra credit. If you think you can read one of these spectrums, you should try and do one of the free response questions, because I'm giving you points for whatever you get right on those things. So even if you only get 1 point, it's still extra credit, like it'll still boost your grade. So the people who did extra credit last week now have grades of like 130 to 140%, because that's how the grades are set up this advisory. So that's not a bad thing to try and do if you're looking to get an A for term 4 to boost your overall average. You should try some of these. So the exit ticket for this class is that, and I will type it up in here. bit.ly/chem3c. So there it is. So once you've picked up the link for the exit ticket, unless you have any questions, that's it. You're free to go.
I miss Bash.
Bye, William.
Bye, Ms. Baskin. Have a good day.
Bye. Have a good day.
Thank you. Have
Go
a
out
good
in the
day.
sunshine. Go out in the
Bye. Have a good day.
Baskin.
Bye. Have a good day.
Miss Baskin.
Yes, dear.
Every time I try to put in the link, it never works. So I have to go on the YouTube.
Why does it not work? What does it do?
I don't know. Like I type every single letter and it doesn't work, which is so weird.
Is the capitalization correct? It has
Yes.
to be a capital HC and then the lowercase HEM 3C.
I don't know why it does that, but oh well. Okay. Bye.